Sure.
Yeah.
What kind of questions, like category?
No, I cannot tell you everything from first chapter to the last chapter, but I gave you a hint already. I said at least 50% after midterm 2.
Okay.
Okay, yeah.
And you have a SRAM problem in it. SRAM.
Okay, yeah.
Okay, thanks, Professor.
My goal is hopefully you study everything. If you try to catch what to study, it will be very dangerous to you. Okay, so please make sure that you study everything, right? Because within the question, I can have question related to others. What I'm saying is just that on average, 50% come from after SRAM, after midterm 2, and we have SRAM question. I want to do this because sometimes people will think this is the last topic I don't want to study. Okay, that's why I give you this hint. But do not try to guess what are the questions, unless you really don't have time. Okay. Now, so now I want to talk about the static noise margin. What is the static noise margin? Let's go back to this inverter, right? If you remember, for example, this is the node A. Node A is the input. What is the VTC? It's something like this, right? So you see, what we did in the beginning was so boring, so cumbersome. I guess some of you might say, why I need to study the VTC? Why I derive so many equations? Because every complicated logic breaks down to that. When you go from A to B, you have this VTC, right? And we actually did that before already, but I just repeat here. And then if you go from B to A, now the B as input, the output, now the B, this is B, I should say this. This is B as output, this is A as input, right? How do you draw the B as input? That is here. Maybe I should do this. As input and then A as output, right? So, of course, you just flip it by 45 degrees, right? Is this okay? And this gives us something called butterfly curve. On the right, you see that I have two butterfly curves. One is the dash one. This dash one is the so-called whole butterfly curve. It means that, or it called creation, which is what we call whole. It means that the word line is equal to 0. The SS transistor is off. Okay, remember in the SRAM, we have the SS transistor, right? So this is 0, this is 0, that is off, right? So I have this dash curve. And then I try to fit into the largest square I can fit in. This is the largest square I can fit in. Okay, and the size of the square give me the so-called static noise margin. Is this clear? I'm not sure you can appreciate how important it is for this static noise margin and the relationship with VTC. Let's look at a bad one. If I do not design my inverter well, I can have a VTC like that, correct? Can you tell me what's the problem with this one? Right? Let's say this is VDD. Is the PMOS stronger or the NMOS stronger for this VTC? Right, we learned about this before already, right? Is the PMOS stronger or NMOS stronger? Do you remember? What you have this in the, say again?
Wouldn't the NMOS be stronger?
Okay, you say NMOS is strong. Can you explain to us why? Why you say so?
What I was thinking was since it doesn't take much for the curve to drop to to 0.
Mm-hmm.
I was thinking that sorry, I'm having some trouble trying to phrase this. Since it doesn't take since there's a sharper, since the curve is closer to like the y-axis,
Right.
I think like the way that you explained it during lectures was like if it moves closer to the left, it's NMOS stronger, and closer to the right, then it's PMOS stronger.
You're right, right? Because just a little bit of V in, we can easily to make V out to ground. And remember, this is just a resistor divider, voltage divider effect. If your NMOS is very strong, it's just like a wire. Of course, you can go to ground very easily, right? So this one is NMOS stronger. Right? Now, if you ask me, you see, these are the basic, right? Can I ask this in the midterm for SRAM? Of course I can. Don't you forget how we do the read and write? Right? So I hope that those who did not answer is just because you don't want to answer. Otherwise, think carefully. We just mentioned in the last class. I already told you why we want to, when we do the reading, right? How do we calculate? How we should size the pull up, pull down, and SS transistor. And that is like what he just said. I need to have a stronger pull down transistor in that context, not exactly the same, right? Not exactly the same context. But if you cannot analyze this, how can you analyze the SRAM, right? So that's right, NMOS is stronger. If I make another curve, I need to flip it 90 degrees, right? So I will have a curve like this. This is a very bad VTC because the largest square, not rectangle, I can fit in is only this much. This is the static noise margin. It's basically telling me that this SRAM is very susceptible to noise, right? So that's why we want to have a more symmetric VTC in order to maximize the square inside. And that is called static noise margin. Any questions? If your question, you should ask now instead of, and I can guarantee to you, right? Even everyone understand here, half of the person who don't come to the class, I assume they watch the video. At least half of them not really understand. You are helping them, right? So if you don't learn anything from this class, I hope at least you learn that you want to learn on the spot. In the future, in your meeting, don't be shy to ask questions. Of course, you don't ask because you did not pay attention, right? Because you don't know if maybe the speaker talked about that already. You ask that and people know that you did not pay attention. Otherwise, you really should ask. And actually, most of the time, people appreciate your question, right? Very often, the VP is there, someone present, 30 engineers over there, 20 engineers don't know what's going on, and they're typing on their computer, right? You ask, you stand out actually, okay? So this is static noise margin. We have another static noise margin called read access static noise margin. This one is the solid line. You see the butterfly curve is very different and it has a smaller noise margin. I will explain later why, right? For now, let's only look at this whole state static noise margin. So this is the whole static noise margin. This is the read static noise margin. I think this is useful to you because in the future, you will all see these terms when you are working, if you still deal with the SRAM or something related. And there is another not mentioned here called write static noise margin. So we have three static noise margin, and usually this is the worst. So if you want to study if a SRAM is good, right, you optimize performance, You optimize the power, you optimize the area. What else? You optimize the cost, but you might have a very bad static noise margin. That is not good. Right? So this is related to reliability. Okay. So what's the meaning of the square? It's not easy to understand actually, but I take this paper when they introduce this static noise margin, so we can have a feeling of that. First of all, remember what we are talking about is what? Regeneration. CMOS is a regenerative logic. This one we mentioned at the very beginning, right? Very beginning. Why CMOS is so good? If I have an inverter, and then in particular in this SRAM case, I have a noise. Let's say this was 5 volts, and it becomes 0 volt. And then I have a noise. This may become 0, may becomes 1 volt. But 1 volt into this inverter will still give me 5 volt. Right? Because even you have the noise, my inverter is good enough that I will bring you back to very close to 5 volts very fast if it is ideal, right? If not ideal, just root a few more. Eventually it goes to the 5 volts, right? Let's talk about this curve again. You have learned that before. I hope that you can draw it. I'm not giving hints, right? No hints. We are not doing this in the final. But as an engineer, if you cannot draw this, then basically you don't know, you don't understand CMOS. You don't understand SRAM. If I'm the interviewer, definitely will ask someone to draw this. If you have due to some noise, you come to 1 volt, right? This one is going to bring me to here. And then this is the output, very close to 5. And then if this one is the input to the next one, then it is here. Then it will bring me to here, right? So you see, after a loop, even I have noise of 1 volt, I'm very close to the 0 already. Okay, regenerative. But this regenerative action won't last. If the curve becomes this, it was like this, right? This was old technology and also general. So you see that it does not go to VDD. But let's say original, this was the butterfly curve. Okay. Let's say due to some reason, it becomes this. It shifts. I shifted this curve. This HY, I shift to here. Right? This curve becomes this curve. No more regenerative, right? Because you see that once I don't have this window, I cannot regenerate anymore. Because if I have a noise here, right? Let's say due to the noise I have here, and then I go up, I reach this point, and this is the output, right? And then I go back, this becomes the input of this guy. And then it will come here. Right? So it's going away to the bistable point. Your signal got distorted. So I don't want to go to details. The basic message is here. If this is the case, if I have noise, let's say I have a noise, it is equivalently to shifting this curve to here. So how much does it need to shift in order to touch it? I need to, if I have a bigger square here, I shift this by this amount, and then shift up by another amount, then you will lose this regenerative feature. And that's why we say that this is the noise margin, the edge. Sometimes people talk about diagonal. So that is okay. For example, this book, he said the static noise margin is on the edge. Sometimes we define the diagonal as the static noise margin, but it's just the same order of magnitude. The point is that if I have the noise, right, it's going to make this out, and then this noise cannot be subdued, and you will screw up the data. That's why we draw the square and say that the size of the square is the static noise margin. Is that clear? Any questions? Now, then we don't. Now I want to talk about the last topic about the read access static noise margin, right? So let's remind ourselves how you do the read. Can someone tell me how you do the read? Do you still remember how we read the SRAM? Forgot? What do we do? The first thing, right, is charge the bit 9, or maybe let me use the top one, right? The first thing, charge to the bit 9 to VDD and bit 9 bar to VDD. I charge it to VDD and bit 9 bar to VDD. Okay. Then what do we do next? Do you still remember? And let's say this store 1, this store 0, right? It can be either of them, right? Do you still remember what is the next step? How do you read it? You need to turn on the access transistor, right? You make this to be VDD. So this is on, like a wire, right? Okay, now still remember what we did to read it? How do I know the left is 0, right is 1 when you read it? What will happen? Just don't even think about what I said in the last lecture. Just think about now I give you this circuit, right? If even you are the freshman, undergraduate freshman or undergraduate student, you have not learned SRAM, I give you this circuit. Can you tell me what will happen? VDD, VDD 0, VDD, VDD, VDD. One means VDD, right? What will happen? Can you tell me?
I mean, it's happening so fast. So if 1 is at the inverter, you have 0 coming out, and then 0 going into the other one, you have 1 coming out. So it almost seems like it would make sense the other way as well if you were to put.
Okay, hold on. Can you say again? Now, this loop is always 0 and 1. You're right. But now I turn this on. What will happen?
Turn just this one, the bit line B on and bit line off. Is that the scenario?
B on. No,
So you're
no. Let me
saying bit line bar.
Let me say again. We pre-charge the bit 9 bar to VDD and bit 9 to VDD. They are pre-charged to there. Okay, it's not connected to VDD, but pre-charged to VDD. Now we turn on the word line. What will happen? How about let me ask you, this is VDD, this is VDD. What will happen? What will happen to this system if all are VDD? But what will happen, including nothing will happen, is also an answer, right? So what will happen? Or now let me simplify the question. Do you think anything will happen? Or when we say happen, I say anything will change, or you think there will be something changing or nothing will be changing?
If all the terminals of the transistor are at VDD?
Given this condition, can you tell me Anything will change. Don't think too deep, right? Just think about this. VDD, anything will change. And then you think right about, or what will change? It means, would this go to 0? Would this go to 0? Would this go to 0, right? If they don't go to 0, it means nothing changed. So do you think it will change? Anything will change?
No, I don't think so.
You don't think so, right? Why?
Because everything is VDD.
Everything is VDD. Now go back to here. Anything will change.
No, same thing.
Why?
Same. It's the same as the right side. Everything
I
is
think the
VDD.
0 becomes VDD.
Yeah. So there are two possibilities. You either charge this up to VDD, or this one will pull down VDD to 0, because there will be current flowing, right? So there will be potential divider effect. So if you just look at this, maybe you feel that no, but we have finished E224. When you see this inverter, you know it is formed by a transistor already. It's no longer the elementary cost for digital circuit. This is 0, this is always 0. No, right? When this is 0, it means the output is 0. It means this is 0, right? This is 1, it means this is 1. So this is off. This is off, first of all. And now you have VDD here. And you have 0 here. Right? And how you get 0 is because you don't have current. But now you turn this on, so current will be flowing, correct? When you have a current flowing, remember in the slide, I said this VL is going to be the R of PDN1 divided by R of PDN1 PDN1 plus R of PG1 times VDD. Right? So then this won't be 0. It will gain certain voltage. That is one thing, right? Second is, remember this one will just pre-charge. So it's actually, here it will be confusing to you, right? Pre-charge for regular read. For regular read, it's just pre-charge, it's just a capacitor. So you are going to reduce the VDD, you keep drawing current, this one will keep reducing. Make sense? Everyone makes sense? Very important, right? Don't ask me to give you hints, but when I say something, you really make sure you understand what I'm talking about. They are all hints. Hints is everywhere. I hope that you really don't just treat this class as something to take GPA, right? So if this is the pre-charge to a capacitor, don't look at this clamp yet, because this one is for the static noise margin measurement. That's why we clamp it. But in regular reading, pre-charge for regular reading, we pre-charge it. When I turn this on, isn't that this should go to ground? Make sense? Anyone object? Anything not clear? I'm giving you hints. Or hopefully you not clear, please say it. I need to pick person, right? So Omi, you just answer me. Sorry, then I will pick you. Is what I'm saying make sense?
Yes.
Okay. So this one will go to, that's how to do the read, right? So you start with 2 signal line. Refer to my last lecture. Bit 9 bar and bit 9, they all start at high VDD. Once you turn on the word 9, what happened? Bit 9 bar will go down and bit 9 will stay the same, right? And then what do? Do you remember how you detect the difference between these two? I spent a lot of time to discuss that. How do you detect the difference of these two? Remember the very complicated circuit we discussed last time?
The sensing amplifier.
Sense amplifier. Yeah, then you pass this to the sense amplifier. You amplify the difference. Then you know whether bit 9 bar is 0 or not. Because if the 0 is at bit 9 bar at the left, then you know bit 9 bar will go down. If it's on the right, then this bit 9 will go down. Then you know what's the difference. Okay.
The sense amplifier is just like a comparator, right?
A comparator, a latch type, or the single-ended differential pair. Remember, I have 2 of them.
Okay.
Yeah. Okay, so here I review what is the read operation, right? And in particular, remember this one. Then why I want to mention this one. We need to make sure this one smaller than the VTH of PDN2. When I'm reading, yeah, I pull down this voltage, but this one go up also. If this guy go up then larger than the VTH of PDN2, I'm going to turn this on, and then that's a problem. This one turn on, this one will go down, right? The high voltage. Then it will come back to turn it off. Regenerative. Then I flip the charge. So just now someone asked me what I'm going to test in the SRAM. I say, make sure you understand every word I said, all the operation, how it operates. Okay. Don't tell you what I'm going to test, right? I don't have many SRAM slides, and all of them are very superficial. Yeah, I have some equation, right? But I'm not going to ask you to write those equations. That is meaningless. Of course, I can ask you to write the form, right? But I'm not going to ask you to solve it numerically for a complicated system unless it's easy to solve. Okay. So I hope you know how to do the read, right? Now, then what is the read access static noise margin? It's talking about when you're reading, what if you have some noise source? Will it flip it, right? So that's why we have a testing method. So this is when we clamp it when doing static noise margin measurement. Okay, so in real situation, in real reading, this one is not clamped, this is pre-charge, like what we said last time. And then you discharge it to detect. But now we are doing the measurement, right? So why we have this VTC? Look at this. I start this at 0, right? So what I'm going to do is to have the input voltage here V in as the input. Okay, so this is V right, right? V right as input, right? So when this one go up, it means, look at this, it directly apply to this transistor. But this is off. Remember, this is off. So what will happen to the V left? Remember, this is VDD, this is VDD, and this is 0 at the beginning. And when it was 0 at the beginning, then of course, the output is VDD, right? And then gradually, when I increase it, then it will decrease because now this output will drop, right? Because this is talking about V left. So this curve is V left as output, right? So you will drop, but this is not a regular inverter because both of them are NMOS. So you will drop and it won't drop to 0, right? Because when this reach VDD, this is also VDD. Both are on. There's a potential dividing effect. And that's why you will reach C instead of 0. Okay. This voltage is just equal to VL equal to VDD times R PDN1 divided by R PDN2 plus RPG1. But that is during the testing when we write equals to VDD for this point, for C, right? And that's why you have this curve. Now compared to the whole one, you see you go all the way to 0. But for the read access curve, it is just up to here. Right? Then we apply the same thing to the left. So basically just flip it by 45 degrees. Then you get another curve, right? And because of this, you have a much smaller square. So the read access static noise margin is usually the worst. So we will compare this when you really do the design, right? Okay, it's not easy. What I'm saying is not easy, but I hope that I explained to you what is a static noise margin. You know how to do read, you know how to do write, and why static noise margin reading is different from the whole static noise margin. Let's pause this for 2 minutes, right? I'm not going to review SRAM anymore from now on. The rest is reviewing. Any questions? Make sure you understand everything. And even you did not pay attention in the last class, this is not a meeting, right? I don't see who is talking actually. Just ask the question. It's just a review. You have not studied, of course, you don't know anything, right? Why don't you understand now? Any questions? Everything is clear? Okay, in particular, I want to show you that if we have this noise, right, then the curve will shift. Although here you have a larger window, but here you actually almost close. Then you don't have static noise margin, right? Then this SRAM is not going to work. But by doing this, we say that the static noise margin of the original curve is 138.3 millivolt. Okay, if clear, then I will move forward, right? So let's review what we have done in the whole class, right? I think this is a good summary. First of all, remember that we have